Hello, everyone. Today we will continue with our lecture about data. We will be reviewing um, information theory measures. So the last time we talked about similarity measures. We will now review measures on information theory and also for comparing objects, and also we will look at density-based measures. So that is when we are plotting our objects in space, we want to see, we were measuring last time how close one object is to another. For the purpose of data analysis, we would find that allows us to find similar objects and group them together. And so we have looked at several measures, including Euclidean distance, Manhattan city block distance, cosine similarity, and Jaccard coefficients for binary objects. So now we will look at some information-based measures and also density, which means we're just going to find dense regions on our plot. So the dense regions are the ones that have a lot of objects in the same place. So we could group the objects just by determining how dense the regions are, and when a lot of objects are in the same place, we know that they're similar to each other because their attribute values are similar. That's why they are plotted in the location that they're plotted in. All right, because we're using the attribute values to create that plot. So we can use information theory as a similarity measure. For example, entropy-based measures would be using information theory. So some similarity measures are based on information theory, would include mutual information, maximal information coefficient, and then probability. So when we're using probability-based measures, we'll talk about the information that relates to possible outcomes of an event. So let's say what will happen. We kind of are predicting what is going to happen. For example, if we take a coin and we flip it, we could get either heads or tails. So what is the probability that we will get heads versus tails? And the probability is 50-50 pretty much, because There are only two possibilities here, either the heads or the tails. So when we're flipping a coin, the probability of getting the heads versus the tails is 50%, because there are only those two options are available. So it's either one or the other. Each one gets 1/2 chance. Another thing to mention here is this kind of probabilities is not very good, because this is pure randomness. You see, there is no way to tell. It's half and half, either one or the other. From information theory point of view, this is not a very good probability. If it was 40%, 60%, then, well, one side has a higher chance than the other, so we can try to make a decision or have a better chance to determine what the outcome of this event is going to be. So the more certain the outcome, the less information it contains. That's why it says here, if the coin has two heads, then the outcome provides no information. The smaller the probability of the outcome, the more information it provides, and vice versa. So entropy is information theory-based measure that allows us to calculate based on probability, the chance that we would have a certain event occur. This can allow us to do data analysis for example, when we have to make a decision. So we would like to answer a certain question, let's say, is this customer profitable for us or not? Or if we're calculating the risk for giving a credit card or a loan to a customer, is this customer high risk or low risk? So the entropy can allow us to answer this kind of question. For example, if we build a decision tree that's going to give us the answer of the question we just asked, is the customer high risk? If we are to give them a loan, then we could use the entropy as a measure of building this decision tree. So this can be used for data analysis, for building decision support systems. For example, a decision tree. It can answer questions such as, is this customer profitable? Is this customer at high risk or low risk for giving them credit card or loan? Okay, so the entropy can be used to determine how to split the decision tree. So let's see here some example entropy. So like we said, the entropy is using a formula based on logarithm. So it is minus probability logarithm based to probability. Now here we are computing the entropy for each class label. In this case, class label is a color. So we have 1, 2, 3, 4, 5, 6 colors here. And we are computing the entropy. That is, we're going to, if we are to choose one of those colors to give us the highest information gain, we could use the entropy to make that determination. Choose the color that gives us the highest information gain. we can compute the overall information gained for this data table by adding them or summing, taking the summation. So if we are to compute the overall information gained for this table, we would add them, you see, adding one. And like we said, we would like to choose one of these attributes that gives us the highest information gain. So we could compute the maximum information coefficient. So we looked at several methods for computing the similarity between the objects, including the Euclidean distance, Manhattan distance, cosine similarity, and Descartes coefficients for binary data. Another way to determine the similarity or define groups of similar objects is by using the density. So, as we explained last time, we are plotting our objects into space for visualization purpose. So if we have, for example, if we have two attributes, each one of those is a dimension, and we use the value for that attribute to plot the object. For example, if the value is 1, 2, 3, 4, then between 1 and 4, then we would plot, let's say if the value is 2, then the x-coordinate will be 2 for this object, and if the value is 3 for the other attribute, then the y-coordinate will be 3 for the second attribute, and that's how we plot the object space. If we have more than two attributes, so if we have two attributes, we would have two-dimensional space. If we have three attributes, we have three-dimensional space. And if we have more, like 4, 5, 6, then we'll have 4, 5, 6-dimensional space. So the number of attributes is the number of dimensions. So once the objects are plotted into the space, the density would tell us regions on the plot that have lots of objects close to each other. When they're close to each other, it means that they're similar. Why? Because we said that we're going to plot the objects at the place 2 on the x-coordinate if he has a value 2 for that attribute. This means that any objects that have value 2 will end up in the same place on the plot if they have 2.1, 2.3, 2.5, they're going to be very close to the 2 there. So we would have a bunch of objects in the same place that have value 2 or close to 2. So for that reason, the notion of density is closely related to the notion of proximity. And because the dense regions are showing objects that are in close proximity to each other. So for certain data analysis methods such as clustering and anomaly detection, this is very useful. So the last time we have seen the Euclidean distance. So we could have Euclidean density or probability density. Here are the objects. See, the objects that have value 2 for x coordinate are going to be right here where it says 2 for x. All of these objects on the line of 2 have a value 2 for x. Now, the ones that are slightly to the left or to the right, they have a 1.9 or 2.1, all close to 2. So this entire cluster here, that circle on the left side, all of these are objects that are close to each other. We have 2 clusters here. One circle to the left and one to the right. So let's spend just a minute here to think about why we would call this here a cluster. There's one cluster here, and then there is another one over here. So look for a second here and look on this density map on the right side and see if you can determine why do we have 2 clusters over here. So the map on the right side is going to show us the number of objects in this location. We can see here. This is a dense region. Or we are looking for dense regions on the plot. So the first one is called grid-based density. And the second thing is showing us the counts for each cell. Euclidean density is measuring the number of points with a specified radius, within a specified radius of the point that we are interested in, or the center point. So we have one point in the center, and then there is a circle around it. So the radius of the circle, if there is any points inside of the circle, they are within the radius. So we're going to count the number of points within the radius that is within this dotted line here. And that gives us the Euclidean density. So we've been talking about measuring similarity or distances between objects for data analysis purposes, and also because we were describing the objects in the data. We said that for relational data, we would have rows and columns, and on the rows are the objects, and on the columns are the descriptions of those objects, which are also called attributes or features. So the objects themselves, we were measuring their similarity based on the attributes or the features. As we wanted to describe those objects. Now, before we start analyzing the data, there is an important step that we need to take, which is called data pre-processing. That is pretty much the preparation of the data for analysis or for mining. So we're going to perform certain operations on the data to prepare it for analysis. So these are several important things that need to be done before we start the analysis. And really, pre-processing is very important step, and it takes a lot of our time and effort for the data analysis task. And it the pre-processing maybe takes 60 or 70% of the time of our time, and the actual analysis would only take like 30%, because the data has to be very well prepared for mining or analysis. In order to obtain meaningful results. So here are several things that we would do to prepare the data. Aggregation. Aggregation is when we are adding data together. That is where we'll be combining two or more attributes into a single attribute or object. This, we would like to do this if we want to reduce the data, if we want to change the scale, or to have a more stable data. So the scale is also called the granularity of the data. So for example, we want to, we have some addresses in the data. These addresses have low granularity. This means if we want to have some report that combines the entire state of California or the entire Southwest or the entire East, Southeast region, then we would change the scale. Instead of looking at specific address, we could look at zip code or state only. So this way we are aggregating the objects. Another technique for pre-processing is called sampling. So sampling, we kind of did this last time. When we were converting the continuous attributes to discrete attributes. Remember when we talked about the temperature attribute while you were doing the exercise with discrete and continuous attribute? And we said that temperature has an infinite number of values. If we're measuring the temperature between 60 to 61 degrees, it goes 61.1, 61.2, 61.3, and all the numbers in between. Infinite amount of temperatures as it moves from 1 degree to the next. But we don't care about these infinite temperatures because we need to have enough space in our computer to store all those temperatures, and nobody cares about millions of numbers between 60 and 61. They just want to know if it was 60 degrees or 61 degrees. And if that's the case, then this is called sampling. We're going to take a sample at 60 and another sample at 61. And we're just going to record those two numbers instead of the infinite numbers in between. So it is a technique for data reduction. And it allows us to convert, let's say, analog pictures to digital pictures or sounds or other attributes like temperatures. It's a natural phenomena. Really, the natural world, natural phenomena has continuous attributes, infinite number of values, and we need some way to save those in the memory of our computer. So we're going to do the sampling and measure only specific numbers that we're interested in. And the rest of the information is lost. It's lost because we don't want it or we don't need it. Or we are reducing the number of data that we are saving. We could also take a small part of the data and do preliminary analysis on that. This is also called sampling. So those two are very common reasons why we would do sampling. Here are some visualizations of the samples. The more samples we record, the higher quality we would have, or we would have more information saved. So let's say for MP3 music, for example. You might have seen something called the MP3 file is 128 bits per second, or it's 64 bits per second. Or 32 bits per second. That changes the quality of the sound, right? As you are listening to this music. However, the size of our MP3 file is much smaller if we have a 32 bits file. Than the 64-bit file than the 32-bit file. Same situation here. This is a picture. We're gonna convert this to a digital picture that has a certain amount of pixels on the picture. So let's say this one has 8,000 pixels. And you can see much clearly here the objects on the picture, that is the dense regions. And if we take 2000 pixels for this one, this is what we would see. And if we take 500, we still have some information. We can kind of tell those shapes here, but they are very weakly defined. So obviously, the more samples that we record, the higher quality we will have, and we would be closer to the original information that had an infinite amount of values in it, whether that's a picture, video, music, or temperature that we're measuring, or some other attribute. So there are different, mostly statistical methods for doing samplings. There is simple random sampling with and without replacement. And then there is stratified sampling, where we would split the data into partitions and draw random samples for each partition. And we've been talking about those dimensions. So going back to our methods for data preprocessing, we have talked about aggregation and sampling. And now we'll talk about dimensionality reduction. So we said that dimensions are the attributes. The if we have two attributes, we have two-dimensional space. Three attributes, we have three-dimensional space. Four attributes, four-dimensional space. Five attributes, five-dimensional space. 48 attributes, 48-dimensional space. That's a lot of dimensions. Really, the more dimensions that we have, the slower our algorithm would run for data analysis. Whether we are building a decision tree, a cluster, or doing classification, or some other method for the analysis, the more dimensions we have, the slower our method would run, because it has computational complexity is increasing. So we always want to reduce the number of dimensions that we have. That is, we as the experts of the data are going to look at this data carefully and see which attributes do I need? What is my goal here? I'm trying to determine Am I trying to determine if this customer is profitable customer? Am I trying to determine whether I wish to give loan to this customer? So whatever our domain is and our goal is, we need to look at those attributes and determine the ones that are the most important in order to answer our question. So let's see, looking for high profitability customers, or whether we should give a loan to those customers or not. Whatever we are trying to answer, we should remove certain parts, certain attributes that are not needed in order to answer our question or to accomplish our goal. So we can look carefully at those attributes or dimensions and remove some of them that are not necessary for our analysis. So this is called dimensionality reduction. This is also called feature selection. We're going to choose the features or attributes that are best suited for our analysis. And it is important to remove the ones that are not needed because, like we said, the more attributes we have, the slower the analysis would run for us. So that's also called the curse of dimensionality. It's called a curse because the more dimensions we have or more attributes, the slower the analysis for the data would run. So that's why they're calling it here curse of dimensionality. This is showing here how the performance decreases as the number of dimensions are increasing. You can see steadily it goes down here. So if we remove some of the attributes, we would avoid the curse of dimensionality. We would reduce the amount of time and memory required to do the analysis. And it will be easier for us to do the visualization. We can easily imagine a two-dimensional space. We just have the X and Y coordinates, and we plot the objects into space. Three-dimensional space we can visualize as well by placing this X, Y, and Z coordinates, where the Z coordinate will give us the depth. We could, like now, if we reduce the number of dimensions, we would, let's say if this is a picture of music, if we're sampling, the more samples we take, the higher quality will be closer to the original. If you need data, the less samples we take, the quality will get distorted. So here, we would choose specific attributes that work for us. So we could select out of the entire data a subset and do preliminary analysis on the subset. We want to remove the redundant features and duplicates. We want to remove the relevant features, that is the ones that are, we only gonna keep the ones that are important or related to our analysis, and the rest that are irrelevant should be removed. Going back to our list of pre-processing steps, the next item that was listed there is feature creation. They could be attributes that we don't need, and we would remove those. It's a very important step for us, but it could be that even we looked at all the attributes, we cannot find the one that is going to help us for our data analysis. In that situation, we could create one attribute. So this is called feature creation. Create a new attribute that can capture important information in data. So we could do feature extraction. We could do feature construction, mapping of data or mapping of data into new space. here we have a picture showing the sound. The Fourier transform allows us to convert from time domain into frequency domain. The first thing here is the time domain. The second is the frequency. That is, it tells us which frequencies are part of that particular sound. And how many do we have? Discretization is another very helpful technique because it allows us to create intervals. So let's say we want to determine if the customer is profitable or if we want to give loan to these particular customers. And if he has like 1,000 descriptions, or 1,000 possible answers to our questions, we don't really care about it. We don't want to have that many values. So we're going to do this. Take objects that have values between 0 to 1,000, and instead of the value 0 to 1,000, record interval 1. Any customers that have a value for the attribute between 0 and 1,000 would be recorded as interval 1. Then we can have interval 2 from 1,000 to 2,000, interval 3 from 2,000 to 3,000, and so on. So the discretization is the process of converting a continuous attribute into ordinal attribute. So this discretization is very useful for classification, like we were trying to determine if the customer is profitable or not profitable, or if he's a high risk or low risk for giving him the credit card. So it will help us to create this kind of intervals because our algorithms run faster as they have less number of values to deal with. So we are getting rid of 1,000 values here and saying, all this is interval 1. I'm going to only record this as interval 1. This is a very popular machine learning database. The plants, iris plants, that is a flower. And there are 2 or 3 types of those flowers. There is Iris setosa, Iris virginica, and the versicolor type of iris. We could look at this iris data as a visualization for the methods that we described. So if we are to use discretization, we will place the values into intervals, and it allows when we plot the data would look similar to this. And here we would find 3 clusters. Here's another visualization that shows the colors. And there are 2 outliers that are outside of the main clusters. Those need to be looked at carefully. Other things that are done for preprocessing are called normalization or attribute transformation. So let's say we have most of our attributes within these values 4, 5, 6, 7, 8, 9, 10, between 3 and 16. And then there is one attribute that has values like 1 million, 3 million, 5 millions. See, this one with the millions is very different from the others. All of them are between 4 and 15. So we don't want to have that one with the millions. We're going to do normalization. And instead of 1 million, we will say 1. Instead of 2 million maps to number 2, 3 million maps to number 3, 4 million maps to number 4, so that the $1 million attribute would be looking the same as the rest of our attributes. So we could normalize the data like this. That would could be called an attribute transformation. So the next time we will continue with our data analysis and discuss some important methods for data analysis. This time we've been mostly defining the data and the data types and studying closely the objects of the data and how they are described and how similar they are to each other. And now we have looked at some pre-processing techniques to prepare the data for mining. So next time we will start looking at the actual data analysis methods.